Good afternoon, everybody. Today I'll be talking about the second formwork design lecture, which is design of slab formwork. So first, in order to understand what is the formwork system, we need to review what you took before last course in Science 4 to 3 about the slab formwork system. Slab formwork system is mainly consisted of decking, which is either ply form or plywood. This is the thing that's directly in contact with the concrete. Then supported by joists, which act as secondary beams. Then the joists are supported by stringers, which act as the main girders. Then the stringers transfer the load to the shores, which act more like columns. So the first step is to calculate your load. Second step is to decide the decking size. Third is determining the safe spacing between the joists, which is the span of the decking, then designing the joists, then determining the safe spacing between the stringers, which is the span of the joist, then design the stringers, then finally design the shores. Our design criteria here is classified into two main families: stress design criteria and deflection design criteria. There are two types of stresses that you could face here: bending or shear, and there are two types of deflection that you should design for: relative and absolute deflection. So typically, because we are talking about wood in general, these are the four design criteria that will vary from one type of wood to the other. I mean, in terms of the values of the stresses allowable and the values of the moduli of elasticity that will govern the relative and absolute deflections. So your reference, that the chapters that are available online, you will see tables like these, like this one, summarizing the critical span due to bending that may cause failure due to bending or shear or absolute deflection or relative deflection. So you will basically calculate four spans and you will pick the smallest of the four, because the smallest will be the one that will initiate the failure, at which the failure will be initiated. You will not reach the highest one. You will fail at the first one that will cause failure. So, but again, you must be very careful when using such equations, because if you look at the footnotes, you will find that here it's mentioning this is an equation for allowable span length for a certain number of spans. So you must be very aware that the equations will change, whether it's a single span or a double span or three or more spans. The equations will change because the values of the bending moment will change, the values of the shear force will change, the values of the deflections will change. By the way, this is applicable now when we're talking about decking, and it will be applicable again when we talk about joists and stringers. And also, you need to refer to the tables that we have referred to in the last lecture, tables 4.9 and 4.11 for physical properties, and tables 4.10 and 4.12 for the allowable stresses. And again, because here we are talking about the decking design, your load here is represented per linear feet for a 12-inch strip. This is again very similar to designing a slab, which is you are designing per unit width. So here the unit width is 1 feet. Of course, a lot of people will find it very tedious to use a lot of equations, use 4 equations to pick the smallest number. However, you will find something here. This is somebody here who did the homework for you. He already did the calculation and summarized it in this table. So for a plywood thickness, certain thicknesses, all the standard thicknesses, he gave you for each support spacing the maximum allowable pressure that it could withstand. And the difference between the numbers between parentheses and the numbers that don't have parentheses into them is that, as mentioned in the footnotes again, the deflection is limited to span over 360 of the span and span over 270 for the values between parentheses. Why could you have two different diffraction criteria? Because in such a case, depending on the usage of the place, maybe you will allow in some cases more deflection than in other cases. So if what we call the architectural concrete, you do not allow deflections in something in a slab that somebody could see. So if somebody could see the floor above him, so you should not allow apparent deflections within the concrete slab, within the beneath part of the concrete slab. People would not like that architecturally. However, for a structural concrete, you could allow a little bit more. So if you have a full ceiling, you could allow larger values of deflection. So the case for span over 270, this is for structural concrete, and the case of span over 360 is for architectural concrete. However, again, you must be very careful, is that also according to footnote number 3, here he's telling you plywood continues across 2 or more spans. And the title of the table, even the caption of the table, it's mentioned recommended maximum pressure for ply form class 1. So he's talking about a certain type of ply form, and he's saying that the values per square foot with face grains across supports. So again, he's talking about something very specific. So here's somebody used numbers specific for a certain type of ply form with certain supporting conditions. He was very specific. He solved the equations for you and he gave you the numbers. So you should be very careful. And again, there is something very important to know here. That table does not include the absolute deflection criteria. So this table, it summarizes 3 equations. But the 4th equation for the absolute deflection, which is actually 1/16 of an inch, is not included in such a table. So let's take a nice example here. Determine the maximum spacing of joists for a concrete floor slab that will be formed with 3/4 inch thick plyform decking. Total design load on the slab will be 150 pounds per square feet. The deflection criteria is span over 360 but not to exceed 1/16 of an inch. And then he's telling you what the type of the plyform and which tables you should use. So you simply go and get the material and physical properties from the tables. Then from the other table you'll get the stresses, the allowable stresses. Then you start calculating your spans. So the first span, which is due to bending, it came to be 26.5 inch. The one due to shear is 68.9 inch, which is very typical, by the way, to find bending to be more critical than shear. Deflection should not exceed spans over 360. This gives us a span of 21.9 inch, which is very common to find deflection governing the stool. And the 1/16 of an inch gave us a 22.1 inch span. So now we should pick the smallest, hence we'll say is 21.9, but again you will never tell a labor to space something on 21.9. So here in the specs it was mentioned to be spaced at 18, that the joist should be spaced at 18 inch on the centers. That takes us to the design of joists and stringers, which are very similar. This is why we'll be only talking about it once, because they are very similar in terms of design steps. So again, here you have one of two options. Either you will be given the load on the decking member spacing, its size, grade, and you'll determine the maximum span of the member, whether a joist or a stringer, which is the most common option because typically you know the type of the formwork you have. Or you will have vice versa. You will not know the size of the member and you will have everything else given, which is not that common. Typically you have your formwork and you know it. And again you have the 4 deflection criteria, the same 4 deflection criteria. However, now the equations will differ, again depending on the number of spans that we are talking about. And again, somebody did the homework for you he gave you these tables, and he will give you so if you once you know your load and you know the sizing, you will get the maximum span. And again here you need to recheck the deflection. So this is a very nice example. He's telling you that the load is 150 pound per square feet, and the spacing is 20 inch, and he gave you the type of wood, which is 4x4 number grade 1 grade Douglas fir larch. So you go and you get the section properties, and you get the material properties, and you get the factors CF and CD, and so you get FB, which is CF times CD multiplied by the reference value, and FV, which is CD times the reference value and the modulus of elasticity. Then you'll get the load, which is the pressure multiplied by 20 over 12, so which is the spacing 20 over 12, and this is the spacing in feet. So now you have the load in terms of pound per linear feet. Then you will get the first span, which is the bending span, to be 71.7. The shear span is 183. The two deflection spans are 60.1 and 47. So now we could find that the 47 inch will govern. So this will be the distance that you will be specifying to the contractor to work at. Finally, shoring design. It's very important to understand that the most critical issue for shoring is buckling. So here we are talking about the effective length, and if you return back to the design courses, the effective length is mainly depending on the end conditions. And the end condition in our case, it's mainly a hinged thing. So because it's typically a hinged thing, this is typically the effective length is equal to the length in most of the cases. And based on that length, you will have different percentages of that effective length. Different percentages of the load that is mentioned here, depending on the dimensions that you are choosing. Also, it's very worth to note that we have other types of forms that are commercially available. They are what we call patented forms, something like table forms that have different configurations. By the way, that stuff is not you are not obligated to know. You are just for your general knowledge, the table forms and the other patented form types. So these are different configurations of that stuff, and each manufacturer will give you the tables that you could use in order to determine for a certain slab thickness what is the appropriate configuration to be. Same thing for wooden truss forms, it has its own tables. Same thing for the steel props, which are the other equivalent option of the shores. Instead of having wooden shores, now you have steel props that could have much higher structural capacity.